Hey Internet, this is Chris from Modka Games with another code warm-up. This time we're going to be doing some advanced programming. The language is C++, but there should be a bit of stuff for everyone. Let's jump right in. So today, what we've got is a basic format for the code warm-up. We take some code from the internet, which has got some defects, and we try and make it a little bit better. If you're doing this for real, please check your licenses. So the language here is Java. We're going to be converting to C++. Basically, this is a good example of test-driven development. So the idea is someone came along here and they wrote all the tests to generate the prime factorization. They wrote the tests and then they wrote the code and they wrote more tests and wrote more code, and we get code which looks a bit like this. So it solves the problem, but it's not really clear how or why, and the resulting code's not that readable. So we're going to try and make it a bit better today and see what we can do. So the first thing we're going to do is we're going to convert it into C++, and we're just going to strip off this Java class. We don't need that. And we're going to change the return type, so the equivalent in C++ looks like this. I'm just going to pop that back down. Now, the function is currently called generate. So when I think of generate, I think of a function like xrange in Python. So xrange doesn't return a range of numbers. It doesn't return 0, 1, 2, 3, 4, 5, 6. It returns an object, which is a generator, that when you call on that function, you get the numbers back in sequence. It's kind of like a big O thing, A generator has a small amount of memory, but you amortize the cost over time. So I prefer a function named like calculate, or maybe compute, or something like that. So we're going to calculate the prime factors. Actually, let's make it compute. We're going to compute the prime factors rather than generate them, because a generator should really return an object. Now, because this is modern C++, we can put this on the left-hand side here. If we're targeting a embedded system, or we're using an older compiler, we might need to actually put the argument inside there to avoid the copy. And if we see that as a problem on a profile, then of course we should do the same thing. We should actually make sure that we're not copying that vector around. So what have we got here? So we're creating a new array list and putting it into this object here. So one technique I like to do is just to have a variable called result. And anytime you see this name result, what that means is we're going to return result. And it just keeps it really simple. So when you see result, you can just kind of think compute prime factors, and result just returns the name of the function, whatever it happens to be. So now we're really starting to drill in here, and we're getting to the meat of this function, which is this scary double loop with no initialization condition here. It's a little concerning because we see this and we just really have no confidence that this is going to complete, this loop is actually going to terminate in a finite amount of time. So what we're going to try and do is we're just going to try and pull this loop apart. We're just going to make a copy of it and see if we can change it into a simpler loop. We know here our termination condition is actually n greater than 1. So while n is greater than 1. Actually, sorry, one more thing I should have done. We have our for loop, and we really need to put the braces in, just like this, or else we can get hung up with our with source control. When someone else adds another line, then they could have made a change here, and we're not quite sure who's changing what, and we can avoid some problems by always putting the braces in when we have a for or an if statement like that. Anyway, so we're going to grab our condition, which is while n is greater than 1. And what are we going to do if n is greater than 1? Well, we're going to start off with candidate is 2. Okay, that's all good. And sometimes we're going to increment it, and other times we're not. What's the condition? So if n is, here's the condition right here. If there's a remainder, we're going to increment. Otherwise, we're going to divide through by candidate, and we're going to add that into our results list. So already we've got this kind of scary double for loop, and we've converted it into something which is a lot more manageable and readable and understandable. It's still not quite clear that this is actually going to terminate in a finite amount of time, but at least now we can see what's going on. So let's just take a bit of a closer look here. So we like less than's more than greater than. It's just a bit easier to read. So if n mod candidate is equal to 0, now we know an if statement has an implicit not equal to 0 into it. So we can actually remove this equals 0 and just flip the sense of the if statement there and just keep it same complexity but just less stuff on the screen. So this is kind of interesting. We should probably check our inputs as well. We know that we can't reasonably compute the prime factors for a negative number. But what about for the n equals 1 case? So the compute prime factors for n equals 1, well, 1 is a prime number, so it should just return back that result. Now what happens is we come down here to this while loop, and this is actually going to do nothing. It's just going to pop straight out. And this is kind of interesting. It's one of the flaws of test-driven development. You write your tests, and you often don't go back. And if you see, like, so for example, the prime factors of 4 is 2 times 2. Prime factors of 6 is 2 times 3. And that's our invariant here. So the invariant is if we multiply the results, we should get the answer. And if you look at the test case for 1, there's actually a faulty test here, which is causing our function to be thrown off. So the correct answer is the prime factors for 1 is indeed 1. Now, if we come back up here, we could do a special case for n is 1 and do some funky stuff there. But instead, what we could do is we could just, let's see how this is going to work. We could append n when we know we've found it. Now, how's that going to work when candidate is less than n? Now we need to kind of invoke some theory here. So what we're actually doing is these aren't just regular candidates, these are actually prime candidates, because what we're actually doing is we're testing for primality here. We're computing the prime factors. So there's no point in doing a candidate which isn't a prime number. So this is actually prime candidate, and this is going to start off at the prime candidate of 2. We're testing when the prime candidate is less than n. If there's no remainder, then we can divide it in, and then, you know, this actually has to be a prime here. And if not, well, what we really want is something like that. We really want it to be the next prime, so 2, 3, 5, 7, and so on. If we have access to this function, and there's a good chance we do, we can just call it like that, or some other way of generating all the primes. If not, we can leave this like this and just have this as a comment, which tells us, anyone coming along, what this function is really doing. So, you know, we're starting to get a bit more accurate, a bit better function here. We're still a little concerned about this. So we know, for example, if n is large, if n is a large prime number, we're going to be doing a lot of work. We're going to be doing like n divides here. When we know that if n is like a large number, that you know, like if n is like 81, for example, 81's a poor choice. Let's say 49, right? We know that 49 is equal to 7 times 7. But if somehow we got to, you know, 7 times 8, well, like there's kind of like a square root factor in here, right? So it's actually like prime candidate times prime candidate. And just like that, we like made a square root of the number of divides we're going to be doing for n is large. So, you know, of course, we could do this this optimization here too if we had that function. And I think what we should really do too is we should just find prime factors by trial division is the name of the algorithm, and that just allows anyone to come along and just improve on understand the algorithm and just verify that this will actually terminate in a finite amount of time. So obviously we need to actually go and run this algorithm just to make sure that it is working correctly and test it. Obviously I don't have the test harness set up, but that's what you want to do next. But I think we've kind of demonstrated how we can turn a pretty some kind of test-driven development code which solves the problem but doesn't really elucidate what's going on underneath the actual algorithm, and we can turn that into something that's just a bit more reasonable and just kind of really shows the algorithm there, shows ways for it to be improved, and it's just kind of a more holistic way of looking at the problem. Anyway, that's all for today, so I hope you enjoyed it. Let me know in the comments below if you have any questions or comments, and talk again soon.